Hello, my humans, and welcome to our very first screencasting of our self-paced unit. Yay! Bear with me, it's going to be a crazy ride, and we're going to just try our best to get through these notes together. So to start, first things first, our unit for the first week is the conservation of matter and phase changes. The first thing we have to ask ourselves is, what is matter exactly? And matter is literally anything that has stuff inside of it. So let's get started and look at our first page of notes. So on the first page, you want to set it up and you want to make sure that you have the conservation of matter and phase change as your title for that first page. My book says that it's page number 17, so if you have that same page number, please put it in the bottom right-hand corner of your page. If your page number is a little different, that's okay, as long as you make sure you keep track of those for your own reference. So when we're talking about the conservation of matter and phase change, we have to understand that mass is the amount of matter in any object, right? And we can see by my picture here that mass is measured with a scale. A lot of people can contribute mass and weight to the same idea, but what we really have to take a moment to understand is mass is the amount of stuff inside of something. So for example, when you're hanging out with your friends on Earth, your mass is the same and your weight is the same. However, if you and your friends were to all go up to the moon, your mass would still be the same mass. There's still the same amount of stuff inside of you. Your weight would be a little different though, because it's the amount of force or the amount that gravity is pulling on you. And we know that there's less gravity on the moon. So when we talk about mass, we have to understand that mass is the same wherever you are. Now, the conservation of mass is the idea that matter cannot be created or destroyed. It can only be changed or separated. When we talk about this, we understand, you're like, wait, Miss Perez, but today I made a sandwich, right? But you were actually putting matter together that adds up to a new product, right? But we're not making anything new per se. And a great example of this, the idea that matter can't be destroyed, is a fire, right? With a fire, we see firewood and we light it with a match or we light it with some oil. And when we put that fire on, we can see that the wood is burning and it appears to disappear, right? And by the end of the night at your bonfire with your friends and your buddies, you can see that, oh, the fire's all gone, right? But what's actually happening there is the matter in the firewood is being changed into something else. It's not being destroyed, it's being changed into carbon dioxide, oxygen, and ash, right, that's left over. So when we're looking at that conservation of mass, we have to see that matter cannot be created or destroyed, but it can be separated or changed at any moment. So when we're talking about the conservation of mass and matter, what we have to look at is what are our different states of matter, and that's what we're going to talk about next. So when we talk about our states of matter, what are the three that you know? Go ahead, take a moment, say them out loud. Let's do some Dora the Explorer stuff in here, right? So what three states of matter do you know? Well, let's turn the page and see if you're right. So for our first state of matter that we're going to talk about, we're going to talk about solids. Yay, solids. And when we talk about solids, we know that we've got lots of examples of solid, right? We've got tables, chairs, floors, doors, everything around us that we can physically touch and hit and mess with is pretty solid, right? And when we talk about solids in a scientific way, we have to talk about the fact that they are matter with a defined shape and a defined volume. So when we're talking about these defined shape and a defined volume, we know that if we took a block and we threw it across the room, that block would be the same shape unless it was harmed or damaged, right? But it's still holding its shape and it's still the same amount of stuff inside, the same volume. It fills the shape the same way. With a solid, we can see that the particles are all packed really, really tight together, just like I have on the left-hand side of my notes here drawn in this picture. And the reason that they are packed together is because they're really tightly bonded. They want to be close together, and they start to vibrate in place, right? Because all atoms want to move, but because they're so closely packed together in a solid, they're going to move slowly and vibrate against each other, right? And so while we're seeing that, we've got some examples. Wood is a great example. It's a pretty nice, thick piece of solid. Ice is a great example. When we're talking about phase changes, we'll talk a lot about ice, water, and water vapor. So knowing that ice is the solid form of water is pretty important. And we also know that metal is a great example of a solid as well. Our next example of a state of matter is a liquid. When we talk about liquids, we all kind of picture water automatically. Personally, I picture Kool-Aid because your girl loves some red Kool-Aid, right? Some of you might also think of hot chocolate or one of your other favorite drinks. When we think about liquids, we know that they're free-flowing. They move around pretty easily. If you took a water bottle and you swished it up and down, that liquid would move from the bottom of the bottle to the top of the bottle as you moved up and down. So when we think about liquids in a scientific way, we have to understand that liquids are matter with no defined shape, but they do have a defined volume. What this means is that you can pour a liquid out anywhere. If you spill a glass of water, you still have that liquid in the same volume, but now it's taking a totally different shape. So the difference between pouring a gallon of milk into a bowl of cereal, like this crazy cat is, you can see that that milk takes up the volume inside of the container, and it changes shape when he drops it outside of the container, but he still has the same amount of space being taken up by that liquid, right? If we were to do some volume equations, we would be able to see that. With a liquid, the particles move freely within a container or outside of their container, but the important thing to recognize is that they stick together. The particles in a liquid want to stay together, but they can still move around on their own as a group. Do you know what I mean? And so some great examples of liquids, again, water, soda, hot chocolate, any of those things that you can recognize as being wet or being in a cup typically. So that's our definition of a liquid in a scientific manner. All right, so now let's talk about the third phase of matter, gas. When we talk about gas, unfortunately, it still is counting as the kind of gas when your dad asks you to pull his finger and all of a sudden there's a real loud noise and a real gross smell. Same kind of thing. A gas is any kind of particle that is moving freely in the air that is not a solid or a liquid, and gases are defined by the idea that those particles spread out and move very quickly with each other. So when we're talking about a gas, one of the hardest things to understand is that gas is literally everywhere. As I'm talking to you right now, I am exhaling gas. While you're sitting here listening to me, you're inhaling gas. Water vapor is a gas, carbon's a gas, oxygen's a gas. Helium, which you fill balloons with, is a gas. Hydrogen is a gas. I mean, we're just surrounded by a bunch of gas, right? And we also know that the sun is a big burning ball of matter and of gas, right? So when we're talking about gas, what we have to understand, it is matter with no fixed shape or volume. Gas can fill up any kind of container. For example, the gas in my lungs could go into a balloon. As I'm expelling it into the balloon, it's starting to fill up that balloon. It's expanding the space in which it's in. I tie up that balloon and I close it, and then all of a sudden someone pops the balloon. All of the gas that was previously contained inside of that balloon can now disperse throughout the entire classroom. So there's no definite or fixed shape or volume. The molecules in a gas will want to spread as far as they can, and they're kind of like introverts. They don't want to deal with anybody, so they're going to kind of bounce around anytime they meet someone new. They'll fill any container up and they'll make sure to spread out as far apart as each other as possible. And again, we want to know that gas particles move quickly. When you let a balloon out, when you let the air out of a balloon, it's going to zoom across the room all crazy. And that's because the gas is expanding and expelling itself and separating as quickly as it can. Some examples again of gas are water vapor, helium, and oxygen. Let's summarize our states of matter. We have solids, liquids, and gases. Some of the features of solids, they have a fixed shape and a fixed volume. When their particles are moving, which all particles are still trying to move, right? When their particles are moving, they're just vibrating against each other. They're not making anything crazy. With a liquid, the shape can change depending on what container it's in, but there's still a fixed volume, right? So when you pour a liquid out, it's still the same volume as when it was inside of the container. And then we have our free movement of the particles. They're kind of flowing past each other, but they still want to stick together. They still want to be around each other, right? In contrast, we have our gas where there's no fixed shape or volume. Everything's kind of free moving on its own. And we know that they move quickly and they're pretty far apart. They're spread far apart. They don't want to touch anybody. They just kind of want to sit on their own in the front of the room away from everybody else, right? So that is our summary of the states of matter. So, to give you a quick overall look at our notes for this first part of our unit, you can see that we've outlined mass, the conservation of mass, states of matter, solids, liquids, gases, and then, of course, we went over a full summary of all of the above. This is what my notes page looks like by the end of our session here. So let's dive into what happens when these different phases change. When matter moves between one phase to another, what are some of the names and the words that we have in science to describe those changes? The first thing that we have to recognize is that a phase change occurs because there has been some change in pressure or in temperature that causes or catalyzes the phase to change from one phase to another. This is also always a result of energy increasing or decreasing within the particles of matter. So, our first phase change that we're going to discuss today is melting. And we all know that some of our favorite things that melt include ice cream and snowmen. Typically, when the introduction of heat happens with something cold, you begin to experience melting. So, this is the change from a solid to a liquid. For a solid to reach its melting point, you have to increase the thermal energy of the particles within that solid. As the energy increases, the particles within that solid begin to move quicker and then become what we understand as a liquid. Those particles begin to speed up and allow those particles to kind of move around. So when ice is melting, we're going from a solid to a liquid that is more free flowing. Up next, we have freezing, which is the opposite movement. This is when you change from a liquid into a solid. To reach freezing point, we have to see the molecules slowing down and a decrease overall in thermal energy. So everything is kind of moving slower. And this just kind of makes sense, right? When you're going in the wintertime and you're going outside, you feel cold, you're tired, you don't want to move around as quickly. But when you're in the summer, you want to run outside, you want to play, you want to ride your bike, you want to do fun things. But in the wintertime, we're all just a little bit lazier. Same thing goes with the particles inside of a solid, right? So, as we're going from a liquid to a solid and we're cooling down, we're decreasing that thermal energy, and all of those particles within that liquid are slowing down to the point where they're just kind of stuck together, vibrating against each other. Moving on to vaporization. Sounds like the word that we use when we describe destroying aliens and using laser guns, but actually, it's a word that scientists use quite often to describe the increase in thermal energy that happens in a liquid that causes it to change into a gas. When we talk about vaporization, this might sound a lot like the word evaporation, and in fact, evaporation is a form of vaporization. The big difference is that evaporation is a slow process that happens at the surface of water after a gradual heating. So you often think of evaporation with a puddle outside, and the sun comes out, and it's a warm, hot day, and that puddle eventually disappears. Well, it didn't just disappear, it evaporated into the air. But when we're talking about vaporization, it can happen in a much speedier way, especially when we think about boiling water. When you boil water, the liquid molecules begin to increase in thermal energy and their particles begin to speed up. So, one by one, these particles begin to gain enough energy to escape liquid state and become a gas. Sometimes this can happen, one particle at a time, and you can see some steam begin to rise before you even have water boiling. Once water begins to boil, which is our boiling point, we see a kind of a flat line in the increase in temperature. The temperature stays the same during the boiling point, but leading up to it, you have that constant increase of energy. Once everything is boiling, it's going to maintain that exact temperature until everything has been become a gas. So, again, just to kind of review our vaporization, it's the change from a liquid to a gas. It's all about the boiling point and the increase of thermal energy when the particles speed up and escape their state as a liquid. Last but certainly not least, we have condensation. This is the change from a gas back into a liquid, which is kind of the reverse of what we've talked about before. Condensation is responsible for a water bottle sitting outside in the warm heat, getting little drops of liquid on the outside. So, what's happening here is that the air, the liquid or the water vapor in the air, is cooling down enough to create this little droplets of water on the outside of your cup or water bottle. So, this gas is now cooling down, the particles are slowing down, there's a decrease in thermal energy, which then results in a change from the gas to a liquid. Condensation is also responsible for the creation of clouds. In the sky, when water vapor begins to cool down, it condenses into a thicker version of that water vapor, which is much more visible in the form of clouds. As the condensation increases, the clouds begin to grow heavy with water and water vapor, and then a result of that is rain or snow, depending on the season. So, that is our basic understanding of condensation change from gas to a liquid, particles slow down, decrease in thermal energy. To get a quick rundown of the phase changes we've talked about today, we have the motion from a solid to a liquid being melting. And if we return that motion, a liquid to a solid is freezing. When we're going from a liquid to a gas, we are boiling, we are increasing thermal energy. If we're going from a gas to a liquid, we're condensing that gas, making it come together into a liquid form. To be honorably mentioned, we have deposition when you go from a gas to a solid. This is in a very extreme circumstance where the particles of a gas slow down so very quickly that they skip the liquid phase overall and turn straight into a solid. In contrast, in a solid, we can have sublimation where the particles that are stuck together in a solid become so very quickly excited and added so much thermal energy that it then becomes a gas immediately. Those will not be tested, but they are an honorable mention and an important extra piece of information for your reference. So here's a quick review of my page. This is what you should have in your notebook. Remember to get a grade of 5 points for these notes that you've taken during this video. Please come up, see Miss Perez, and I will check that off in the grade book. To continue on to the next section, our knowledge check, please use these notes to help yourself be successful. We have finally made it and we are done with these notes for the day. Let's see what we can do with this knowledge.